118, varbūt mēs varam tur kaut kā izmakt tos datorus vecos. Šodien nākamā eksāns atgādinās.
Man sākmīt.
Konkrēti laiku kopā. Tas, kas nav uzskaitē, tad ir taču ir pērā. Tas, kas ir uzskaitē, viņš tur vēl kaut kādu ceturtai pentiju. Ir mini, pārāk mini. Man jau ir uzdevums tāds. Ir neuzticams atcerīgais.
Es? Tikai minimum ir vergu komandā.
Jā, un tad August tā, ka ja mēs ātri iztīrīsim, tad atradīs naudu miljoniem datoru. Tad mēs jau visu kā ielikām, bet viņi vēl iedos ļoti ļoti.
Jā, iedos, ja būs kaut ko problēma. Tā, kur es esmu? To do something. To do. Jā. Tā, iespējams pat tā ir planēta. Tā, nu, kur viņi ir? Oops. Works fine. Wait, my DXT. Yeah, works fine. Okay. Need to do something. I have a plan for today. And what's the plan? I need to tackle one important moment. We will not go further without some knowledge on Laplace transform. What I'm talking about? Let's start with simple idea. Let's say I have a network like this. Come on, it's a useless chunk. Ground, switch, resistance, and this will be, let's say, my output voltage. Maybe I'll switch this way. Yeah, here is my output voltage. So my voltage will be 0 when time less than 0. Yes, the switch activated at time 0. And E when time is greater or equal to 0. Very simple kind of signal. Just switch on. So, let's try to obtain a spectral function of this. Let's try to perform Fourier transform. So, I would like to do Fourier obtain spectral function via Fourier transform of my voltage. Sounds very easy. So what should I do? I should perform integration in infinity about not omega. That's what should I do. This means what it will be E integrated from 0 to infinity about omega time in time. Easy, easy, easy. So I will get E divided omega multiplied by f of omega time, and time here I should do it starting from 0 and ending at infinity. Here are my margins. Okay, meaning what I will E divided by omega multiplied by 1 minus, let's take it as a limit of f power, meaning not omega time. Bang. What is a power? Not omega time. It's a rotating vector. Plus 1. Rotates with the speed omega. What limit it has? No limit. It will rotate infinitely. Bang, nothing happens. Why nothing happens? Because the signal do not comply with Dirichlet conditions. Should exist from absolute value of signal and absolute value of its first derivative. This one, yeah, I guess here. This one do not comply with Dirichlet condition. So, appears that it's not possible to perform a Fourier transform. What can we do? We can cry, or we can make it. We can forcibly create a margin. We can forcibly make the signal to comply with the Dirichlet condition. Idea is to multiply original signal with a power minus Ct, where C, this is constant, high enough to create. This was original, this will be multiplied. Forcibly create a margin. We immediately should note one thing. We can analyze only for positive time. Because in negative time, a power minus ct will ruin our left margin. Now, what we will get? We will see interesting kind of spectral function. It will be in reality function of two variables, frequency and selected constant. It's infinity to infinity. Not a power minus a power minus dot omega time to time. Because I have this a power minus ct, here should be 0. So I can rewrite my spectral function as integral from 0 to infinity in a power minus c plus j omega time yes, this is correct. In time. What I got? I got spectral function of plus your omega. This is complex. What is the name for this? Complex frequency. I have here a complex frequency. It contains real and imaginary part. Complex frequency. If we perform inverse Fourier transform on spectral function determined in space of complex frequency, what we will get? 1 divided by double p in infinite margins. My spectral function, a power omega time, the omega equals to original, which multiplied by a power minus ct. To get rid of this, I need to multiply everything by a power ct. To eliminate this term, also, to simplify life, I need to change from the omega to the c plus dot omega. This will help me. This allows me to obtain very needed thing. 1 divided by double p, z minus j infinity, c plus j infinity. Spectral function from complex frequency, a power j omega time d c plus j omega equals to original voltage. Looks like inverse transform. I hope you can see it. It's an inverse transform. Or so-called Mellin integral. Now, one moment. To simplify notation, special designation for complex frequency is used. Or P equals C plus J omega, or S equals sigma plus omega. There is absolute no difference. On the moment, two different notations are used for complex frequency. In reality, there is no difference. Now I can write Laplace transform. So integrate from 0 to infinity 1 t e power t gives me spectral function from complex frequency, or so-called image of my original pulse. Name for this is image. 1 divided 2p c minus j infinity c plus j infinity 1 p image e power pt that p equals to my original voltage. So these are two. This pair of transformation describing Laplacian transform. I can write like this. Laplacian transform from time function gives me image as a function of complex frequency. Inverse Laplace transform from image gives me time function or original. Two important remarks. First, Laplacian transform works only for positive time. Usually, special so-called switch-on function is used. It's in 1 t equals to 0 when time is less than 0 and 1 when time greater or equals to 0. Switch on function 1, it will be green, 1, 0. Switch on function 1 from time. Next important remark. If you have, I know, Laplacian transform. If you substitute P with omega, what will you get? You will get spectral function. So image, one more. Equals to spectral function. Simple. If you have an Laplacian image, put your omega instead of P or S, depends on notation, and you will get spectral function. Laplace transform is a common form of Fourier transform. Now, what's important to know about Laplace transform? First, linearity. Big no, everything told about Laplace transform is applicable to Fourier transform. Okay, linearity. So let's say I have 1 and 2, both time function. Performing Laplacian transform on 1, I got an image, time function. Second is a Laplacian transform result from 2. Linearity means what? Laplacian transform on 1 plus equals to 1 plus u second. Laplacian transform is linear. Transform from sum yields to sum of transform equals to sum of transform. Same is enforced for inverse transform. Also, again, I had uno is a result of Laplacian transform. And if I have A as a constant, Laplacian transform on multiply original A, simple multiply image by constant. Delay. Theorem of delay. Again, image is a result of Laplacian transform on some original from E. If we perform Laplacian transform on delayed pulse, okay. If we perform Laplacian transform on delayed pulse. It's the same what multiplying image by a power minus p tau. Theorem of delay. Very important theorem. Theorem of derivative. Again, image is a result of Laplacian transform. What we will get if we take a derivative? Performing a Laplacian transform on the derivative, we will get you need simple. To get derivative, you just multiply by frequency. But there is one moment. 0 plus, what is this? It's a limit when epsilon, no, 0 plus epsilon. It's a value of your signal or your function or your original at a 0 time. You can easily extend it to any order of derivative. One more. It's integration. Performing Laplacian transform on integral from 0 to time yields us original divided by complex frequency plus epsilon goes to 0, from 0 to 0 plus epsilon, no 0 plus epsilon, the time divided by p. It's a value of integral at a 0 time. In Laplace world, integration is an algebraic operation. time scale change. If image 1p is a result of Laplacian transform of t and a is a constant, also a should be greater than 0. Laplacian transform t divided by a equals to a image from at, time scale change. Okay. Why is this important? It's a very powerful tool to analyze transients. You can perform an analysis on transients with a special crafted network. So I do suggest you should have reference to this book, starting from page 333. You will get good insight into Laplacian transform. You can feed its electronic version to translator. So, if you have resistance in your network, space of time, space of complex frequency, it will remain resistance. If you coil, your coil will become PA, something like this coil, and EMF, this is EL from 0 plus. If you have capacitor, this capacitor will be, how to do it better, 1 divided by PC. And this one is UC, no 0 plus, divided by P. Width should go with minus sign. Oh, minus sign, yeah. You can solve your network in Laplacian space, perform, and in reality, it's an AC network analysis. But the result will be function of complex frequency. Here, A, it will be Laplacian of A. For simple DC, E divided by P. Same with current source. You need to perform an image. Short list of functions. I started with E multiplied by 1 of Laplacian results is nothing less than E divided by P. Its spectral function will be A divided by omega. Because it has it goes to infinity at 0 frequency, you cannot perform Fourier transform directly. Linear growth multiplied by k. Linear growth will have its image as divided by p squared and spectral function as minus 8 divided by omega squared. Popular thing in control systems. Decaying exponent, a power minus alpha, right? Multiplied by time. Starts from is 0. Its Laplacian image is a divided alpha plus t and its spectral function will be something like this, divided by square root alpha square plus omega square multiplied by a power your arc tangents omega divided by alpha. Point divided by R, it's how model spectral function looks like. One interesting object pulse with a length of tau. And with magnitude E. Mass description for such pulse will be E multiplied by 1 minus 1 minus tau. E multiplied by such difference. Its image is quite simple. E 1 minus E power minus P tau divided by P is image of such function. But its spectral function is quite tricky. You can obtain its spectral function and it will be omega tau by half divided by omega tau by half and multiplied by a power minus j omega tau by half. It's a spectral function. It looks like absolute value spectral function. This top is I tau and double p divided by tau, 4p divided by tau, 8p divided by tau minus double p divided by tau, like this. One day you will remember this spectral function. One more. Growing exponent. Growing exponent. 1 multiplied by a 1 minus a power minus alpha time. For such signal, its image in Laplacian space is E alpha divided by P plus alpha. And spectral function, clean some space, will be E of its E alpha divided by square root of omega power 4 plus omega alpha square a power j arctangents, and here will be alpha divided by omega. Yeah, here it is. And one more second. Bit more. For sine omega t multiplied by 1 its image will be omega divided by omega plus p, 1 second, square and square. Yeah. For cosine will be p divided by p squared plus omega. Square. Yeah, but now correct. Okay, I can show it once more. This book, page 333. Remark on inverse transform. we will see, I will show how it do. Inverse key problem with Laplacian technique is obtaining a time function how to perform an inverse transform. We do have technique of numerical inversion. This allows us to perform all the job numerically. Okay, questions? No? No, if no question, I think it's enough for today. I will system with feedback will be next time. Okay?